Okay. Something like this. Sound check. 1, 2, 1, 2. Yes. And
Yeah.
okay. And
This is forward.
this is forward.
No, this is forward.
Which
This arrow, yeah. That is backward.
But this one is forward.
Yeah, maybe that is also forward.
Yeah, I checked. I think we're all fine.
Okay, we're going to do a little bit of introduction.
Yes. Hi, doggy.
Session chairs just back with everything.
Like who is sharing? Prahlad or the dog?
Either way.
The other invited speaker, will start.
Yes.
It's preferable if you point right there so that you appear right on the camera. If you turn back, then you're not visible clearly.
But the camera, you mean, do I have a pointer? There's no pointer.
Forward and backwards, right? And this is the one that you can find.
Which one? I hold it and point, and it will.
It's not going to do a thing.
Oh, it shows. Fancy, super fancy. Okay.
Let's.
This is aging. Okay. Okay, and this is pointing. Okay, I'll try to remember. So look forward all the time.
Let's leave.
Okay, I'll do my best.
Really more people who want to attend yet.
I think he saw the cat, no? I mean.
Okay. Let's start the last talk of the today workshop. We are happy to. He's one of the few people who straddles both these communities. He's good. Jakob did his PhD in proof complexity from KTH, working with Johan Hastad. His work in his PhD was recognized by both the Best Paper Award at Stock, as well as he won the Ackerman Best Thesis Award awarded by EACTS, the European Association for Theoretical Computer Science. Since then, Jakob was then a postdoc at MIT with Madhu, then joined KTH as a faculty. A couple of years ago, he moved from KTH to Copenhagen in Denmark. More recently, Jakob's papers have won the Best Paper Award in AAA as well as the SAT in 2022. Happy to have you, Jakob.
Thank you. Organizers for inviting me. Thank you, Mina, for being the opportunity to have this big scientific party. So this is going to be a talk about graph coloring and algebraic algorithms. It is joint work with Jonas Conneryd, Susanna Rezende, who's in the audience, Shuo Pang, and Kilian Risse. And I should say that I wanted to see if this one will flip the slides. Yes, it will. Okay. So thanks, Jonas and Shuo, for helping me out with the slides. So this is sort of a nice closing talk, slightly symmetric to Madhu's opening talk, in that it's going to be about proofs and computation. It's going to be a little bit more technical, though, perhaps. So you should feel free to stop me at any time to ask me questions so that I can clarify. So this is going to be a talk about coloring, and just to make sure we're on the same page. Like we all know coloring, and you know, I give you a graph like this. I want you to use the fewest number of colors so that all neighbors will have distinct colors, and we all know that it will require 3 colors to color this graph. We can't do it with 2. And this is, of course, one of the original NP complete problems by Karp. It has been heavily studied. For all we know, it's also hard. I mean, it's not only NP complete, it's even hard to approximate. Even if I get a promise that the graph is colorable with a constant number of colors, the best algorithms we have will need a polynomial number of colors. And it's NP hard to approximate essentially to within any meaningful factor. Okay, so at least from a theory point of view, this is a dead hard problem, except that, of course, the practitioners, as usual, they have no respect. They just go ahead and solve this problem anyway. It's very annoying, just as they do with SAT. And so there are a number of different approaches. There are sort of backtracking and SAT-based approaches, approaches based on integer linear programming, and algebraic approaches. And what we're interested in is whether we can prove lower bounds for any of these algorithms. In particular, we'll be focusing today on algebraic algorithms. If, you know, since, and this is not a futile effort, because it's interesting, especially if you focus on the sequence of award-winning work by Delora, Margulies, and others. They write even that their algorithms are so good that they're looking for, like, we haven't found any hard instances yet, basically. So, you know, therefore it's a meaningful question to ask whether we can rule out basically that, you know, maybe they're solving NP in polynomial time and we just didn't discover it. So in fact, we do know that they're not doing this. We do have exponential lower bounds for graph coloring. Okay, so then why can't we just, you know, finish the workshop and go to the workshop dinner? I know this is the last talk that remains. Well, these lower bounds are somewhat unsatisfactory in the sense that they are obtained by reductions from other problems. So in some sense, it's not so clear how much they tell us about graph coloring per se. And I would argue that the graph coloring instances that pop out of these reductions are maybe not necessarily the graphs you would like to cover every day. And in particular, this leaves open the possibility, the absurd possibility, that maybe it's just these pathological instances that you get from our reductions that are hard. Maybe on average, you know, graph coloring is easy. So can we rule that out unconditionally? That's sort of what the question we ask ourselves today. So we want average case hardness results, and these have been known for almost 20 years for SAT-based algorithms, where we know that if you basically sample a random graph, then it will be, and you sample it so that it's not 3-colorable or k-colorable for your favorite k, then it will be exponentially hard to determine this. Okay? And we would like to get the same for algebraic methods, and this is what I want to tell you about today, that algorithms that are based on Hilbert Nullstellensatz or Gröbner basis computations will also require exponential time to solve k-coloring on random graphs. Okay, so
Random graphs that are k-colorable?
So let me get to it in a second overlay on this slide. So what we will do, we'll translate this into a question in proof complexity. So we will look at what these algorithms do, the method of reasoning that they use, and then we'll formalize this, or we'll see that it can be formalized in an existing proof system. And this means that if I take an algorithm, a graph that is not k-colorable, and run the algorithm, and the algorithm correctly decides that more colors than k are needed, then from this algorithm execution, I can read off a proof of non-k colorability, which will be short if the algorithm execution is fast. And now we will prove that no such short proofs can exist. That's the game plan. Okay, so that answers the question. Perfect. So, okay, so what's the proof system? So we'll start off with the so-called Nullstellensatz proof system, which builds on Hilbert's Nullstellensatz. So suppose I have a bunch of polynomials P1 up to Pm in a polynomial ring over your favorite field F. And I want to argue that they do not have a common root. So there's no assignment to the variables. Let's think of them as Boolean, because they will be Boolean today. There is no common root. Then one way that I could convince you of this is if I can find polynomials Q1 up to Qm, so that when I sum up from I goes from 1 to m, qi times pi, and I syntactically get the constant 1, then I hope you will be convinced that there is no common root. Okay, and this was formalized as the so-called Nullstellensatz proof system by Beam et al. Okay, and soundness we just argued clearly, if there is a common root, then the right-hand side would vanish, but the left-hand side kind of will, okay, left and right, what do we have now? For you, it's like the right-hand side won't vanish, the left-hand side will vanish. And yeah, so that's a proof of unsatisfiability. Completeness is not so obvious. If I promise to you that variables are 0, 1 valued, then it follows as a special case of Hilbert's Nullstellensatz, basically. Okay, so this is the basis for our algebraic reasoning. However, these Nullstellensatz proof are not always so efficient, because having to write out this whole explicit linear combination of polynomials, it can be fairly large. So it's nicer if I can build it up dynamically in the following way. So I'm given again my set of polynomials p1 up to pm, and then I'll derive new polynomials either by taking linear combinations from p. If I've derived p and q, then I can take alpha p plus beta q for any alpha and beta in the field, or I can also multiply any derived polynomial by a variable x, and I do this until I derive the polynomial 1. Then it's sort of clear that from this I can construct a Nullstellensatz certificate, but I did it dynamically, and now maybe I can save on cancellations along the way. And in fact, this is an exponential increase in proof power. So we'll study this proof system, polynomial calculus, which in particular models what Gröbner basis computations can do. If you know that, if you don't, then now you've heard the buzzword, and we won't worry about it. We'll focus only on polynomial calculus from now on. What are the measures, the complexity measures that we're interested in? Two complexity measures. The main one is proof size, which I'll measure as the number of monomials in any derivation. So I think of polynomials represented as linear combinations of monomials with some coefficients from the field. So the size of a polynomial is just the number of monomials in it. The size of a derivation is just summing up the size overall the polynomials. And I won't get too much into technicalities, but for technical reasons, it's convenient to also allow special separate formal dual variables for negated literals. So for every variable xi, I will have a normal variable xi and then a dual variable xi bar, and then I promise that xi plus xi bar minus 1 evaluates to 0, so that they take opposite signs. And this is we introduce these dual variables in order not to get strong exponential lower bounds for the wrong reasons. It won't be too important for us, so I won't dwell on this. And another measure that we will be very interested in, which is not affected by the addition of dual variables, is proof degree, which is, again, I look just at the whole derivation, I look at all the polynomials, I look at the largest total degree of any of the polynomials in the derivation, and that's the degree of the derivation. Okay? And now it should be clear for both of these measures, for proof size and proof degree. Oh, there's a question over there? Yes? I'm not, with the mic maybe?
The size of the polynomial is the decrease the size of the polynomial.
The rules can certainly, I mean, if we have cancellations, for instance, right? I mean, alpha times p plus beta times q could cancel massively.
Oh, you have.
Does that address your question?
Okay, okay.
Yeah. So, I mean, I will sort of always, if things cancel, I will cancel.
Okay, nice.
Yeah.
Right. Also,
thanks.
Yeah. One more question, because you're trying to show that three coloring is on most cases, whether it's easy or not. So,
Trying to rule out, so we already have worst case graphs, like I can exhibit explicit an explicit infinite family of graphs where the hardness scales exponentially. This we already know. But now I'm worrying that maybe this is some kind of artificial pathological family. And now I instead want to talk about random graphs, and I'll get to in a minute exactly what I mean by random graphs. And I want to say that if I just sample a random graph, is that easy, or can I prove that actually random graphs are also hard? Because that would prove in some sense that most graph coloring instances are hard. That's the idea.
Yeah, that this property is not almost surely true or false.
Say again?
Is the property of three coloring not almost surely true or false?
Sorry, I can't hear you.
Is this property in the limit? Is it the case that it's everything satisfied?
If you set your parameters correctly, depending on again on how you set your parameters, I won't get into much on this, but yes, there are some kind of threshold behaviors that if you sample a random graph of a certain density, then you're almost sure that it's k-colorable, and above the density, you're almost sure that it's not k-colorable when the number of vertices goes to infinity. That would your question?
Yeah.
Okay.
Yeah. I mean,
Good. So where were we? Yeah. So we'll talk about proof size. We'll talk about proof degree. Clear that once I've fixed a formula, I can just look at all my derivations, and I can take the minimum over proof size and the minimum over proof degree, and that defines the proof size of proving unsatisfiability of a set of polynomials, or the degree of proving unsatisfiability of a set of polynomials, and that's my measure. Okay, good. So let's see how we encode k-coloring as a set of polynomials. So we'll have variables xvi that basically just says that vertex v gets color I. And then we have polynomials. You should think of these polynomials, we want them all to be zero, right? We want them all to vanish. So this first polynomial forces that vertex v gets some color I, and then I make sure, because I'm not sure what characteristic I'm in, I make sure that it doesn't get two colors. And then for neighbors u and v, I don't want them to have the same color, and then I just want to make sure that they're all Boolean. Okay? And now if you're a computational algebraist, you might say that, oh, yeah, so I hope if you stare at this for a second, you realize that any common root to these polynomials will give me k coloring, and vice versa. If I have a k coloring, then I will get a common root. Okay, but the computational algebraist will say that, well, I prefer to instead encode my colors as kth roots of unity. So I adjoin a root of unity to my field, and then I encode the different colors as different powers of a primitive root of unity. It turns out that it doesn't make so much of a difference, because we'll prove degree lower bounds, and there's a linear substitution that takes you from this encoding to the Boolean encoding that we're interested in. So from now on, I'll only talk about the Boolean encoding. Okay? And so now I can state slightly more formally, maybe not fully formally, but what we're claiming is if G is a random graph, it's a sparse graph on n vertices, then with asymptotically almost surely, it holds that a polynomial calculus proof of the fact G is not three-colorable requires exponential size. Okay, this lower bound holds regardless of which field you're in. It holds for both if I have if I sample a random regular graph, or if I sample an Erdős-Rényi random graph. Obviously, I have to choose the parameters carefully. If my graph is too sparse, then the reason it's hard to prove that it's not three-colorable is that it in fact is three-colorable. The theorem remains true, but it's not so interesting. And obviously, if my density goes far too high, so that I have, like, say, Gn 1/2, so I'll get large cliques, then this no longer holds. Okay, so I have to choose my parameters so that this statement is meaningful, but I won't get too much into details. Yes?
Or
This is for polynomial calculus with dual variables. Yes. And the reason I don't care so much about the dual variables is that we will actually establish this by proving a degree lower bound. And then there's a result by Impalazzo, Purlak, and Skal that says that if you have a strong enough degree lower bound, then that automatically implies a size lower bound regardless of whether you have dual variables or not. So from now on, we'll just focus on proving degree lower bounds, and we don't need to worry about size. Okay? So degree lower bounds, what do we need to do? we just need to look at the constant polynomial 1. We need to look at the set of polynomials derivable in degree d, and we just want to prove that 1 is outside. The problem here is that the set of polynomials derivable in degree d can be a very complicated set. So we're not sure how to analyze this. Can we hope to really pin down the structure of these polynomials? It looks like a fairly intimidating figure to me. So what hope is there? Fear not, Razborov told us what to do. He said that we should find a linear operator satisfying 3 properties in addition to linearity. It should map all axioms to 0. It should kind of commute nicely with multiplication, but it should not map the constant 1 contradiction to 0. So what's the idea? The idea is if you look at the kernel of this operator, it kind of over approximates what we can derive in low degree, but 1 is still outside. And the hope is that this over approximation will be nicer to analyze. Okay? So this is our game plan. Let's see. So good. How would we construct such an R? Well, there's a very nice tool, namely polynomial ideal reductions. So let's do a quick recap what polynomial ideals are. If I'm given a set of polynomials, fancy style P, the ideal is just the smallest set that contains all of these polynomials. It's closed under addition, and it's closed under multiplication by any polynomial, even outside, right? So it's a polynomial ring that is closed under multiplication. Why is this of interest to us? Well, if you think about it, the ideal generated by P is precisely all the polynomials that are in fact semantically implied by P, which means that this is exactly the set of polynomials that polynomial calculus can derive because it's implicationally complete. It can derive anything that is implied, which means, getting back to what I said before but didn't prove, that 1 lies in this ideal precisely if the set of polynomials P is unsatisfiable. Okay? And now if I have such a set of polynomials, I can decide on an order, a total order on all the monomials, where 1 will be the smallest monomial. Once I decided on my order of monomials, I'll order the polynomials by their leading terms, by their largest monomial. So now we have a partial order on polynomials, or actually a total order on polynomials, sorry. And then I can reduce any polynomial modulo the ideal generated by P. So if Q is a polynomial, I let the reduction of Q mod P be the minimum polynomial in Q minus R for R ranging over all polynomials in the ideal. And you could think of this as that this is a sort of just a generalization of, say, counting modulo integers or whatever. Like 12 modulo 5 is 2. We're just doing the same modulo polynomials. The minimum polynomial, I'm ordering polynomials with respect to the largest monomial they contain. And then I also like lexicographically for smaller. Okay. And so some basic facts of this reduction operator is that, firstly, well, it's well defined, which I'm proving to you by intimidation, I guess. It's linear. The kernel of this, it maps exactly the ideal to 0. And it's a projection. Okay, so if I apply the reduction to the reduction, then I get the same result back. Okay. And now, just a small example. Suppose that I've ordered, I have a 2-variable set. X is larger than y. I have the ideal generated by the polynomial x plus y. Then basically, if I get a monomial x to the a times y to the b, what the reduction operator will do, it will just replace x by minus y, so that x to the a, y to the b reduces to minus 1 to the a times y to the a plus b. Okay, it's just a small toy example, but so that you can see what's going on. And now the very nice thing, if you think about it, is that this polynomial reduction operator is exactly what Razborov is asking us to construct. Almost. Except, unfortunately, we started with an unsatisfiable set, so we're missing out on one condition. We want to map 1 to non-zero, And unfortunately, 1 is in the ideal to map to 0. Otherwise, polynomial reduction is a perfect, it's exactly what we're looking for. Okay, but it won't work because, again, P is unsatisfiable. So in fact, the ideal generated by P is everything. Yeah, it's a very sad fact. Okay. Again, Razvorov together with Alignovich told us what to do. What we should do is, for every monomial, we should identify a subset, a fairly large subset, but not too large, of axioms. And then we'll just reduce, we'll do an honest reduction, but not modulo P, modulo this smaller set of axiom polynomials. And then we just extend by linearity. So we define the operator for every monomial and extend by linearity. Okay? And the intuition is that somehow this subset S of M for the monomial M should pick the axioms that somehow speak about the variables in M. And the idea is that this operator R should look like the real deal in low degree. Okay? So you could think of it as a pseudo reduction that claims that it's actually reducing modulo P and 1 is outside. And if you're only in low degree, then you can't tell this apart from a real reduction. Okay, that's our intuition. So how will this come about? Again, let me recap what we want from our operator. We want it to map axioms to 0. We want that if I take x times p and reduce that, that should be the same as taking x times the reduction of p and then reducing that. This is, by the way, exactly what what the mod operator should work like, right? I mean, if you're mixing mod counting with multiplication, it doesn't matter. They sort of commute. I guess the formal term isn't commute, but never mind. But note that we're not promising that this will hold in general. It will only hold for polynomials of not too large degree. And then the reason that will prove, and then we want contradiction to not map to 0. Suppose that we can design this R. Let's just convince ourselves why we're done, okay, with our degree lower bound. Well, we start by noting that all the axiom polynomials in the input, they map to 0. They are inside the kernel. And then by linearity, whenever I take a linear combination, that result by induction remains in the kernel. When I multiply by property 2, I also remain inside the kernel, as long as I'm in degree at most d. Okay, so everything derivable in degree d will map to 0, but apparently 1 doesn't map to 0. Hence hence 1 is not derivable in degree d, and we have our lower bound. Yes.
The pseudo reduction, are we just going mono an ideal generated by a subset of the axiom? Or
Yes, but we'll pick. In fact, we'll pick a different ideal for every monomial. So depending on which monomial I'm reducing, I'm going to pick a different ideal. Okay, and now you should start getting a little bit worried, and we'll get more worried in a slide or two. So I think we're not getting worried yet, or maybe we are getting worried. Yeah, we're getting worried right now. Okay, so let's see what happens. So let's just take the simplest property. I have an axiom polynomial P. Let's say it's a sum of two monomials. P is M1 plus M2. I want it to reduce to 0. So R of P should be 0. Okay, let's expand. R of P is by linearity R of M1 plus R of M2. Somehow I've chosen an axiom set SM1 and an axiom set SM2. I'll reduce M1 modulo the ideal generated by SM1 and M2 by the ideal generated by SM2. And now it's sort of, you realize that we're starting to lose control here. We would like this to map to 0, but we're reducing two different monomials modulo two different ideals. And it's not clear what happens at all. Okay, so let's do some wishful, some forceful wishful thinking. Suppose that I can find an ideal fancy style I that contains this axiom P. Okay, It also contains both S of M1 and it contains S of M2. Okay. And furthermore, when I do an honest polynomial reduction, it doesn't matter whether I reduce modulo Sm sub I or modulo the larger ideal I. Why would this be true? Well, in general, it will be very, very false, but suppose. Let's just suppose. Okay. Let's note that if that happened, we would be very happy. Okay, because now I expanded RP to R of M1 plus R of M2, and then I was getting worried because we were reducing modulo different ideals. But now I said, well, without loss of generality, I can reduce modulo I for both of them. And now I'm doing an honest polynomial reduction. So it's linear. So this is reduction modulo the ideal I of M1 plus M2. And note that this is one of the polynomials that is the generators of the ideal. So this definitely maps to 0. So we're done. Okay, how would I find such an ideal calligraphic I? Not so clear, but it would be wonderful if we could do it. Okay. Okay, so we're basically halfway through the presentation, and in fact, all I've done is to sort of try to sell you very nicely packaged old news. Okay, I haven't said anything new. So what I have told you about, it's there already in Alifnovich-Razborov, the 2003 paper. It's been further developed in a bunch of other papers. So sort of what's the problem? Why aren't we done already? And it's a good question. And this is during this second half of the presentation, I'll probably start lying to you more and more. But I'll try to sort of convey some flavor of what the technical problems are. Yes.
So was it the case that those works that you mentioned above actually applied this approach to some polynomial ideals and proved that degree lower bounds there?
Yes.
Okay.
Yeah. So this whole idea of, in particular, they somehow miraculously found these calligraphic eyes, which we'll discuss in a minute. And how does this? Yes, that's another question.
The degree restriction was not there.
Yeah.
Then you would be forced to admit that everything in the ideal will actually reduce to 0.
Yeah.
So where does the degree restriction show up in the?
Oh no. So the degree. Okay. So here's the point. So let's see. So the point is that note that there are no degree restrictions down here. Like here, I'm doing honest reductions. Okay. So why am I safe to, in particular, at some point I will do a reduction for 1 and do an ideal there. And basically now if my subset of axioms is not too large, so I'm picking out a subformula, like a subset of polynomials. If that subset is satisfiable, then in fact 1 will not reduce to 0. Right? So I'm going to be very, very careful so that I'm going to reduce modulo not too large ideals so that everything I reduce modulo is satisfiable.
In the one of the conditions that you had was that if you look at R of X times P,
yeah,
you want that to be, the second bullet point.
Yeah.
Somehow we want to ensure that this holds only for degree D minus 1 polynomials.
Yes.
And that in fact,
I think if I remove that condition, I'm basically saying that R should be an polynomial ideal reduction.
Yeah.
And then I would be screwed. Right?
Yes. So we somehow need to ensure that that condition holds only for low degree, and beyond a certain point it doesn't.
Yeah.
Okay.
This is and like I guess I'm getting ruining all the suspense, but property 2 is really the hard thing, and that's like really where the main technical challenge is. This is what's going to be hard. And you should also, and I'm going to say this in the final slide, but I can also say this is somewhat similar to if you know about sums of squares lower bounds, where you have these pseudo expectations, where you're constructing something that looks like actually an expectation, but only for low degree moments. This is sort of morally similar. Okay, and there's also like if you want to prove Nullstellensatz lower bound, there's a notion of you construct designs which also only work for low degree. That are sort of they are sort of an LP dual, except that it only works in low degree. Kind of, sort of. Yeah. Did that? Okay. So where were we? I think we were here. So yeah. So this has been implemented. Among other things, it has been implemented. The one principle that proof complexity theory obsess about. Okay, yeah, so it's perfect. And the so why can't we do this for the pigeonhole principle? And this is where I will start lying. But somehow, one nice property of the pigeonhole principle is that you can sort of nicely isolate sets of polynomial axioms. In the sense that if I take a few pigeons and I send them to a few holes and I clean up the residual instance, this is still like a pigeonhole instance, but with fewer pigeons and holes. However, if in a similar way I pick a few vertices and sort of color them, then it's not then the colors that I've added start propagating throughout the graph, and it's hard to sort of color just a subset of the graph and then cut it away and say that, oh, the rest of the graph is completely unconstrained. And I'm not claiming that this is a precise technical description, but for me this is like the one big difference, I think, why we have lower bounds for the pigeonhole principle long ago, but why coloring seems so hard. Because in fact, this has been, I mean, it has been open for almost 20 years. It was obvious immediately, I think, since the Beam et al. Lower bound for resolution that, okay, good, now let's do this average lower bound for polynomial calculus. And it just seemed hard. I mean, I've thought about it for a long time and failed, like made several attempts back in, 10 years ago. So what happened? So I should say that there was a paper over on the math side by Romero and Tunchel in 2022, which came with some really nice ideas. They wanted to solve a slightly different problem, thankfully, so they didn't realize that this was applicable to what we wanted to do. So we were happy to take their ideas and use them in that direction. I'll get to that later. Okay, so back to what are we going to do then? Well, we need to define an R operator. And for this, we need to associate to every monomial a set of axioms. And I'll do this by associating to every monomial a set of vertices, and then basically take the sub-formula saying that the induced graph on these vertices is k-colorable. And in a random graph, if I don't pick too many vertices, I can afford to pick even a linear number of vertices, this graph will in fact be 3-colorable. Okay? But the whole challenge is now, when I pick these different vertex sets for different monomials, how do I sort of sync them up so that, you know, locally everything will look fine, but then I'll sort of have to patch things up so that when I start mixing monomials, they will look like they're basically, I have to fake it that I'm reducing modulo the same ideal, although I'm working on many different monomials. And it's not entirely clear how to do that. So how do we do this? So look at a monomial that's like xu2 times xv3 plus xw1. Let me say that it mentions uv and w. Okay? And I'll define something. The vertices related to a monomial I'll define it in 2 steps. First, I'll look at vertex sets in my graph and I'll define a closure operator, which is sort of a larger set of, maybe the vertex set U is not nice, the closure of U is a larger set that is nice in some sense. And then I'll just set the vertex set to associated to the monomial M. I'll take the vertices mentioned in M, which is maybe not a nice set. I'll take the closure of that and the axioms for coloring for that subgraph is what I'll reduce modulo. Okay, and this is getting a little bit technical. It's not too terribly important, but just to say we want 3 properties of this closure. We want it to behave nicely with respect to subsets. So once I define the closure of U, and if I take a U prime that lives in the closure of U, then the closure of this set should not go outside the closure. the closure should not get too large. So if U is kind of not too large, maybe linear, but not too large, then the closure should be essentially the same size. And finally, and the real challenge is it should be also reduction preserving. And you'll recognize this property from before, but I'll strengthen it now to say that for any monomial that mentions only vertices in the closure, and in fact, any vertex set that is not too large, okay? If I take the closure and then throw in the set J, the reduction doesn't change. Okay, and it's sort of clear maybe from the small example that I did before, like if we can get this, then we are in excellent shape. But hopefully it's not obvious how to do it, because this is like exactly, I think, where we were stuck for 20 years. Exactly at this point. Yes?
So, but on the closure of U, you're referring to, you take the graph just on closure of U and the action corresponding.
Yes.
To that and the corresponding ideal.
Yes.
Yeah.
Exactly. So I dropped the angle brackets. I did that a few slides ago, a little bit sneakily, and I didn't say it. Yeah. So exactly. So our subclosure of U is the true reduction operator, which takes, it looks at the vertices in closure U, it generates the coloring formula for that induced subgraph, generates that ideal, and then reduces. Exactly. Yes. Good. So again, the key property is that my closure should be such that if I throw in an extra set of vertices J that is not too large, that doesn't change the honest polynomial reduction. Somehow the honest polynomial reduction doesn't really care about whether J is there or not. Okay? And okay, so now we're getting to a point where, like, I won't be able to go into details, but basically what do we need to do? Well, it turns out that one way of achieving this is that somehow the closure should be so nice that throwing in this extra set J doesn't really add any significant extra coloring constraints. So in the following sense, that if I have, here's my closure, and suppose I know of a coloring, any valid coloring to these vertices, it should be easy to extend to the neighborhood in J that lies outside the closure. Okay? And it should be possible to do this in an order-preserving way. So remember that I need to order my variables in some way. We'll order the variables just by vertices. So we'll have some kind of vertex order. And I want it to be the case that when I color these vertices outside, these colors should only depend on smaller vertex colors. Okay. This is a little bit technical, but you know, we'll soon be done with this. Okay, and this property, so somehow the idea is that given a coloring of my closure, the vertices outside in the neighborhood should be very unconstrained. Okay, so let's think about, and it should be possible that colors should only depend on smaller neighbors. Okay, so here are three bad cases that I don't want. Case one is, well, clearly I cannot color vertex V7 unless I know what the color of V6 is. And this is bad news if V6 is larger. So this I don't want. This will destroy my property. I don't like this structure in 2 here, because here I have 2 neighbors outside, which both have neighbors inside. So actually, it's not clear. I mean, the coloring of these 2 guys will actually depend on each other also. And that's a dependence that I don't like so much. I would like to be able to color V4 and V5 only depending on the coloring of the closure. Okay. And one thing I like even less is this V2 that has 2 neighbors outside, because then maybe actually the color, for all we know, the color of V2 might be forced. Okay, and we might start propagating constraints now. So we don't like these structures. In particular, a closed set should not contain things like this right outside. Okay, so how would we fix this? Oh, and I should say that here is like the first instance where we're really in a crucial way using the insights from Romero and Tunchel. So they also proved coloring lower bounds, but they did it only for graphs that have very large girth. And for that reason, they can never get up to more than logarithmic degree lower bounds. And we want linear degree lower bounds. So we have to come up with something slightly different. And basically, the way they can avoid these properties is basically by using high girth. And we'll have to do something different, and I'll get to that in a minute. So the obvious way.
In your case, it's okay to have a path of length greater than 3 from.
Yeah, and length 3 will not be, I don't remember the parameter now, but I think paths of length 3 or 4 also I won't be so happy with. But 5 would be okay, say, something like this. It's a parameter, basically, you can play with it. Okay. So how would I construct a set that doesn't have these violations? Well, I start with the given set that I want to compute the closure for. And then I don't want smaller vertices outside. So I just follow all paths as long as the vertices are smaller, and then I just throw them into my set. Okay? And then I look, do I have any violations of these properties 2 or 3? If so, I throw these vertices in as well. And now maybe I have some new order decreasing paths, so I throw those vertices in. Now maybe I have violations of type 2 or 3, and I throw them in. And I just keep going until all violations are gone, and that's my closure. Okay, and I would argue that this is clearly, and the closure view is when this process terminates, we're done. That's the closure. Okay, and again, it's getting late in the day, and I shouldn't torture you more, but it's sort of, I think we can agree between friends that this looks like it's probably well defined. Yes, but how large will this set be? That is not so clear. Like this could snowball completely out of control, right? And indeed, this is like another thing where I think ideas like this were around at least 10 years ago, but we didn't know how to control the size. And so, but we claim that we can control the size, that for a random graph with degree d, the parameters are not, okay, so the parameters are not so important, but basically if the original set size of the set U is linear but not too large, then in fact the closure won't be too large. Okay. And here is again where our friends over from the math department help us by telling us which order we should use. Namely, we should take a valid coloring of G, okay, and order the vertices according to the color classes. Okay, and we said, wait, this doesn't make sense. We were trying to prove that the graph was not 3-colorable, right? Yes, but it's a random graph. So if it has, now I'm cheating you a little bit. Let me focus on the random regular graph case. So a random regular graph of degree D will in fact have chromatic numbers, something like D over log D. Okay, and the log is in fact not important. The important thing is that it's constant. So we can get a coloring not with 3 colors, but with D colors for some small d. Okay. And now this will allow us to make sure that these ordering decreasing paths, which are dangerous, that they're not too long. Okay. So if I choose a coloring like this, you can sort of see that the only edges here will go in between color classes. And I can order them arbitrarily so that, say, red is largest, and then yellow, and then green. But the point is that any order decreasing path will have now length at most 4 in this picture. Okay, and there will still be like a blow up by a multiplicative factor d in every layer. Like you see here, this guy, for instance, this red guy can have 3 different neighbors, but it's only happening this blow up by a factor d only happens by a constant number of times. So now we know that when we throw in these order decreasing paths, that doesn't increase size by too much. Okay, but we still need to think about our offending structures. And here the point is that if you think about it, so maybe we go back even, if you look at at the structures like this and some other structures that I'm cheating you on, but Madhu caught me, so you know it was no use. But anyway, I'm not telling you, these are some examples of offending structures. There are some more, but basically, if you look at them, they're fairly high density structures. They have like many edges. Okay, so I can argue that when I throw in these type 2 and type 3 violations, I increase the edge density inside the set that I'm building. So as I'm building my closure and I start with U and then I get U1 and U2 and U3, etc., the density increases and increases and increases. But this is a random sparse graph. It's not supposed to have dense subsets. So that is why this won't snowball out of control. This will, in fact, stop after a constant number of rounds. And then I will have something like, you know, the blow up is again D for every color class, but I only have chromatic number of D colors, and then raised to some power times U. So this is the blow up. And this is again, as promised, this is all a constant. Okay, so this means that now I have defined a closure that is looking nice in the sense that in the immediate neighborhood, I will be able to continue the coloring in a sort of unconstrained way. And the closure is not too large. Why is that important? Well, one reason that it shouldn't be too large is I'm going to reduce modulo closures. And I can't pick up so much on my graph that I get a non-3 colorable chunk, because then I'm dead. But that won't happen. That's what I proved here. Okay? So now the size lemma that the closure is not too large is true. And now let's look at the pseudo reduction operator properties. Now our proof that we did before, where I just said, oh, wouldn't it be wonderful if I could find a slightly larger ideal? Now we can actually do this, right? If I have an axiom P, then I just say, well, an axiom mentions at most 2 vertices. So I'll take that set U, and I can in fact take the closure of that set and add it and reduce all the different terms in my axiom modulo this larger closure. And since this set is not too large, it won't affect the reduction anyway. And obviously, again, if I'm able to throw in P and reducing P modulo an ideal that contains P, then it maps to 0. And then I know that it actually mapped to 0 all along because of this theorem, this reduction preserving property that I had somewhere here, this key property, right? So basically, I just throw in the axiom vertices here, and then I will pick up the axiom polynomial. The complicated proof, which I won't even attempt to do, is to say that the reduction plays well with multiplication. But this is basically just using that the closure is size preserving and reduction preserving, and I use it over and over again for a few times. And I will just basically do, again, it's somewhat similar to what we did before. I'll expand all of these reductions, modulo different ideals, and I'll be nervous for a few lines in my calculations. And then I realize that, oh, I can actually pick a larger ideal that contains all of these. And then I'll move into this ideal, and then once I'm inside this one ideal, then by linearity, I get the whole polynomial again, and I reduce the whole polynomial, and then I'm actually doing an honest reduction, and it behaves exactly as it should. Okay, so then we're home. And that, or the reduction of 1 is 1, well, in this particular case, it's very easy because the constant 1 will have an empty closure, so reduction doesn't do anything. So done. Okay.
Because we're going more the empty ideal, or
yeah, but in fact I could, but it just so happens that we get the empty ideal here. Actually, am I cheating you a little bit here? No, I don't think I'm cheating you. But even in previous papers, like the only thing that is important here is in fact that whatever I have here is a not too large vertex set. I just want to make sure that if I'm reducing modulo 3 colorable subgraph here, as long as that's the case, I'm fine. Because then 1 will not reduce to 0, then it will stay the same. Because 1 is the minimal term. So like either it reduces to 0 or it stays the same. Those are the only 2 possibilities. And it will, and the only way it could reduce to 0 is if I'm reducing modulo an unsatisfiable set of ideals. Because again, you know, a polynomial reduces to zero only if it's implied by the polynomials in question. And one is only implied if the set is unsatisfiable. So we're done, except for all the details, but you know. So what do I want to say? Maybe philosophize a little bit about where we could go from here. I mean, coloring is a nice problem. So we've had lower bounds for resolution for a long time. Now we have it for polynomial calculus. We had worst case lower bounds, I guess, in 2017. Now we have average case lower bounds. There are stronger, or strictly speaking, incomparable, but morally speaking, probably stronger proof systems above polynomial calculus, like Shirley-Adams, that models linear programming hierarchies, sums of squares that models semi-definite programming hierarchies. Slightly incomparable to this, the cutting planes proof system that Susanna talked about. It would be very interesting to get coloring lower bounds. I think even worst case coloring lower bounds for some of these proof systems. I think there are lots of interesting problems also for polynomial calculus. For me, polynomial calculus as a proof system is right at the border. I mean, resolution is so well understood by now that you really need a good reason to be able to publish a new lower bound. As Olaf mentioned, there are still excellent problems out there, like clique is a wonderful problem for resolution. We still don't have a lower bound. But for many formulas, we kind of know how to do lower bounds. For polynomial calculus, we have this machinery that I've described to you, but every time we try to use it, you run into like unexpected technical difficulties. So it's right at the border of what we can do. And every new combinatorial principle that we attack somehow teaches us something where I understand what we're doing. In particular, you can view coloring is basically the problem of can I have can I homomorphically map my graph into a triangle? That's basically what coloring is. Now you can say, well, what about slightly more complicated graph, like a 5-cycle or something? And then it turns out again, this is like, we have strong reasons to believe that this is equally hard, but what we're doing here seems to just break. Clique problem is another great problem, again, already for resolution, definitely for polynomial calculus and beyond. A third problem is a slightly niche or connoisseur problem, but it's there's a dense linear order problem where you encode the following combinatorial principle, that I have a set of elements, they're all ordered, and the order is dense. So if x is less than y, then there is a z in my set that lies strictly between x and y. We know that, and this is obviously, I mean, a finite order cannot be dense, so this has to be unsatisfiable. This is in fact easy. We know for resolution that this is easy, but it's an interesting extremal formula in the sense that we also know that it requires fairly large resolution width. And it would be interesting to understand whether it also requires a large polynomial calculus degree. And either way would be interesting. Again, it seems to be one of the, I would guess that it's hard to see why it shouldn't be hard for polynomial calculus degree. But again, it seems to foil like all our attempts. It seems to break the tools we have at this point. Two more problems. If I lost my pointer, I guess. Do I need to do something? Yes, okay. So there are different lower bound techniques. There are some lower bound techniques that, what I told you now is basically all of these papers that I cited are for lower bound techniques that are independent of the feeds. But then there are also other techniques that work for sets of polynomials where the lower bound, where the hardness depends on the characteristic of the feed you're in. For instance, the Sapien formula will be easy if you're in GF2, but will be hard in characteristic different from 2. And it would be interesting to somehow see how these techniques compare to the techniques I told you about now. And there are certain things that we can do in one setting, but in not the other. And it would be nice to get a unified understanding of this. And I also mentioned that this notion of pseudo reductions is very similar to design to pseudo expectations. I haven't seen anyone like make any clear connections. Like, would it be possible to translate between pseudo expectations and pseudo reductions, for instance? And can we understand what's going on? Okay, so it's high time to wrap up. So again, what did I say? That graph coloring is extremely hard in theory, but for applied algorithms, maybe not so much, which raises the question of whether we can at least rule out unconditionally that the practitioners are solving NP-complete problems without telling us. And the answer is that yes, we can do this in a very strong sense. We have linear degree lower bounds for polynomial calculus, which means exponential average case running times for state-of-the-art algebraic algorithms. And as I just tried to convince you, there are lots of interesting, good open problems in this space that I think you should take a look at. So thanks.
Reduction from other problems like graph coloring in general is improved by reduction from other problems. And later on, we talked about the reduction. So, and then finally, in that the original thing, like, so we use the polynomials and ideal reduction and all that. So essentially, isn't that the reduction itself, like
these are two different, I mean, the pseudo reductions was like a lower bounding tool that we used once I fixed the coloring instance that I wanted to prove a lower bound for. The other reductions that I talked about, the way we proved the lower bound for coloring before was basically, we know that the pigeonhole principle is hard. We even know that it's hard if you limit every pigeon to fly to just K holes. Okay, and now it turns out that you can take any bipartite expander graphs of left degree K, and then you can think of the pigeon flying to its ith alternative as being basically the pigeon colored by color I, and now you can sort of do a gadget reduction to get a coloring instance that is K colorable if and only if you can map the pigeons to holes, and then you can prove that basically, if there's a polynomial calculus proof that this graph coloring instance is not K colorable, then I could use that to also prove that the pigeonhole principle instance is unsatisfiable, but we do have an exponential lower bound there. So those previous reduction results were like reducing different types of combinatorial principles to coloring. Does that answer your question?
So in regards to this question as to, how much are you convincing the practitioners with this thing? It would have been great if we could have come up with a distribution on K colorable graphs such that their algorithms take a long time to find the K coloring, right? Because they're trying to give you a K coloring and it's thing. What we're getting is a distribution on graphs where the resolution proofs will be very long. But these are not K colorable, and they could just put a timeout saying after this much time, if I don't find a coloring, I'm done. Is there any way to infer from a distribution on sort of non-colorable instances to get a distribution on colorable instances where the problem is?
I mean, that's a good question. Maybe two answers. I mean, in some sense, if the optimal number of colors is K, in order to decide that that is the optimum, you will have refuted K minus 1 colorability. So I'm not sure unsatisfiability like this setting is so much of a problem. I think more, though, the bigger problem is maybe that, and for a good reason, they couldn't care less about these random graphs because this is not the type of problems they want to solve. Just as the same way as we know that the random CNF formulas are dead hard for resolution, but the reason that SAT solvers are so useful, nobody wants to solve random KCNF formulas. People want to solve the CNF formulas come from somewhere, and probably the graphs come from somewhere. So to sort of, we don't have a precise mathematical understanding, but I think the reason why combinatorial optimization is so successful in practice is not that they figured out some way of cracking NP, but because these humongously large CNF formulas that they use to verify, say, circuit designs or something, are in fact easy in practice. And why are they easy? Well, because there was some kind of design team that said that, okay, here's how we construct this thing, and we're fairly confident that it's correct. And that means it's not too complex. So somehow I think, I mean, it would be nice to formalize this, and we don't know how to formalize this, but I think also probably for graph coloring, the reason practical algorithms work so well is that they're solving easy instances.
Sorry, I have two questions.
Actually, I have two questions. So, what is that, like this algorithm being able to run for random graphs would, in some sense, depend on how dense the graph is. So, it's like a monotonic property, and those are known to have threshold behaviors. So, the threshold is well than what we start with.
I mean, we know how to set the parameters to get, you will get graphs that are, you know, again, you get asymptotically almost surely lower bounds. And because I think there, I mean, I don't even know it exact value, but there is like a threshold for how high the density should go for a graph not to be 3-colorable. You go slightly above that density, and now you're in a very hard regime.
I see. Also, this reduction from deterministic algorithms to proof, but how about random algorithms to prove complexity? Is there something like that known?
I mean, in this setting, it doesn't really care, right? Because as long as your algorithm outputs, I mean, in that sense, the lower bound, I think, is very, very strong, right? We know that with probability, with asymptotically almost surely over the instance. So once I sample the instance, okay, unless I'm extremely unlucky, it is exponentially hard. Okay, and even if you add randomization to your algorithm, at the end of the day, you will have somehow produced an algebraic certificate. But this certificate has to be of linear degree. And then assuming, which I'm sweeping under the rug, the question is, how are you going to represent your polynomials? Are they going to be as linear combinations of monomials? Apparently, yes, this is what they do. Then we also get an exponential size lower bound. If you have some kind of niftier representation of your polynomials by, I don't know, zero suppressed decision diagrams or whatever, our size lower bound doesn't apply, but it still seems that mostly for most of these algorithms, if you have linear degree lower bound, that implies that they're going to run for exponential time. And so it's like an extremely robust lower bound in the sense that we're not even looking at the algorithmic choices. We're assuming at every time step that the algorithm non-deterministically does whatever is best. Okay, and the exponential lower bound still applies.
Yeah. So I mean, my question is not very well formed. So the pseudo reduction somehow looked like if we locally look at the axiom space, then they're all 3-colorable in some sense, and therefore these reductions make sense. And it somehow reminded me of in the Weisfeller-Lehmann type setup. I mean, usually there is this constructions of graphs which are non-isomorphic, but somehow locally look the same. So like, I mean, is there a connection where can we come up with, I mean, is there a way in which we can say I can construct two graphs that look very similar, but somehow the chromatic numbers are like vastly different? And would that lead to any sort of degree lower bounds in, I don't know, or some sort of...
It's an excellent question. I don't have a good answer. I think one direction that I also didn't mention, and I don't know if we ever thought about it, but you could try to, I mean, one direction in which you could try to push this result is to try to construct or find graphs with higher and higher chromatic number for which ruling out 3-colorability is still dead hard. It's not clear that random graphs will be so good because, as I said, I mean, we kind of know that a random deregular graph will essentially be decolorable. And so you won't get that much of a gap. So maybe if you want to get a larger gap, you'd have to think of other constructions. But it's an excellent question. I haven't thought in this direction at all.
Let's thank Jakob again.
Let's thank all the speakers of the today workshop. Neil has a couple of announcements to make, but before that, let's thank Akshay, Nutan, Olaf, and Prajakta for this wonderful workshop, and of course, Meena for giving us an opportunity to come together for 2 days. And then the local IIT Gandhinagar team for the entire support. Thanks. We have more to come. Over to you, Neil.
All right, thank you very much. Next up is the banquet, and we have an hour and a half to fill. So I'd like to welcome Jyoti from the Center for Creative Learning, who is largely responsible for what you have in the kit. If some of you have no ideas for how to kill this time, we are happy to take you around the center, give you an informal. There's more of a guided tour with more members of the lab joining a little later in the week. However, if you just want to hang out for a bit,